ME 204, Equation of Motion in Cartesian Coordinates. Do you remember your statics? When we had a problem like this where we have a block, say it's 50 pounds and a force pulling on it at an angle of 30 degrees, how did we solve something like this? Well, the first step that we took was to draw a free body diagram, like is shown here, where we have a normal force and a weight and a friction force, and then we break the pulling force into components. Once we have a free body diagram, then we can solve this problem by summing forces in the x direction, setting it equal to 0, summing the forces in the y direction, setting that equal to 0, and summing the forces in the z direction and setting that equal to 0. Notice that in this case, all of our forces are balanced. The sum of all the forces in each direction equals 0. What happens when the forces aren't balanced? When we have forces that are balanced, we don't have any motion. If we have unbalanced forces, say for example we have our block and we have a really large force pulling on it compared to our friction force, which is small. In that case, our block begins to accelerate and moves. Newton's second law of motion states that unbalanced forces on an object cause the object to accelerate. Forces cause masses to accelerate. We can write this as an equation with forces being represented by F equals mass times the acceleration. So Newton's second law of motion states that forces equals the mass times the acceleration. For dynamics, we use the same equations that we had in statics, except that now our forces don't balance. We have an acceleration on the objects, so our sum of the forces in the x direction are equal to the mass times the acceleration in the x direction. Sum of the forces in the y direction are equal to our mass times the acceleration in the y direction. And the sum of the forces in the z direction are equal to our mass times the acceleration in the z direction. Notice that in this case, we have unbalanced forces that cause our accelerations. If we have a car that's traveling along the freeway at a constant speed of 75 miles per hour, what is the net force on the car? Well, if it's traveling at a constant speed, the net force is 0. There's no acceleration that's occurring. If there's no acceleration, then the net force must be 0. So our force equals mass times acceleration equation is equal to 0. How can this be? Isn't the car using fuel? Isn't the engine putting torque on the wheels which are pushing the car? The car is in motion. Well, the answer is that the force on the wheels pushing the car is balanced by the friction and the air drag in the opposite direction. Fuel is used in the car only to overcome the friction and the air drag. How would this be different if the car were accelerating? Well, if the car's accelerating, then we're applying enough force at the wheels to overcome the friction and the air drag, so we have a net force. This would cause the car to accelerate. Now it's important that we understand units when we start working with the equation of motion, F equals ma. For metric, when we have forces equal to mass times acceleration, our forces are in newtons, masses are in kilograms, and accelerations are in meters per second squared. Notice that a newton is not a basic unit. It is made up of different components, kilograms, meters, and seconds. So a newton is a kilogram meter per second squared. We can break down the newton into its base components, but we can't break down a kilogram any further. We can't break down a meter any further, and we can't break down a second any further. What about English units? Well, again, force equals mass times acceleration. And in English units, a force is a pound. Our masses are slugs, and our accelerations are in feet per second squared. Again, a pound is not a basic unit. It's made up of slugs, feet, and seconds. So a pound is a slug foot per second squared. Again, a pound is made up of different components, so it's not a base unit. But we can't break down a slug any further. We can't break down feet any further, and we can't break down seconds any further into any smaller units. You'll avoid a lot of mistakes with units, especially when working with English units, if you always think of pounds in terms of its composite units. When you see pounds force, always write it as slug feet per second squared. That will avoid a lot of problems when you're solving these types of problems. There's some important conversion factors that we need to remember. 1 slug is equal to 14.59 kilograms to go from English to metric units. 1 slug is equal to 32.2 pounds mass. A pound's mass is another measure of mass in the English system. More often than not, we're going to want to work in slugs, and so we'll use this conversion factor to move from pound mass back to slugs. And 1 meter equals 3.28 feet. How do we think of pound force versus pound mass? Well, what if you were given a mass of 30 pounds mass, and we needed to know the mass in slugs? Well, to go from 30 pounds mass to mass in slugs, it's just a simple unit conversion. We're going from mass to mass, and we have a conversion factor of 1 slug is equal to 32.2 pounds mass. So 30 pounds mass times 1 slug per 32.2 pounds mass will give us 0.93 slugs, and our pound mass cancel. What if we were given a weight of 30 pounds force and we needed to know how much mass there was? Is this simply a matter of converting units? In this case, no. Because we have pounds force, it's not a base unit. We can break it down into smaller components. So we have to use our equations. Force equals mass times acceleration, or in this case, a weight, which is a force, equals a mass times gravity, which is an acceleration. If we solve for mass, we get that our mass is equal to the weight divided by gravity. Our weight is 30 pounds, and our gravity is 32.2 feet per second squared. Well, there's nothing here that we can cancel at this point, but if we go ahead and write our pounds as slug feet per second squared, then our mass is equal to 30 slug feet per second squared divided by 32.2 feet per second squared. Now our feet per second squared cancels, and we're left with slugs for our base unit, and we get 0.93 slugs for our mass. Notice that in both of these cases we divide by 32.2, but the thought process is completely different. In one case we're doing unit conversion, and another place we're solving the equation of motion. Let's look at the same example, but if it were on the moon. What if you were given a mass of 30 pounds mass and needed to know the mass in slugs? Well, again, the process is the same. This is a unit conversion. We're just converting from mass to mass. 1 slug is 32.2 pounds mass. So we use our conversion factor with our 30 pounds mass. Our pounds mass cancel, and we're left with 0.93 slugs. Now, what if we're given a weight of 30 pounds force on the moon, and we need to know how much mass there was? On the moon, gravity is equal to 5.48 feet per second squared, as opposed to our 32.2 feet per second squared on Earth. Is this simply a matter of converting units? In this case, no, it's not. Again, we use our equation of motion, F equals ma, or our weight is equal to mass times gravity. If we solve for mass, we get mass is equal to weight divided by gravity. Our weight is 30 pounds. Our gravity is 5.48 feet per second squared. But we want to write our pounds in the base units. In this case, mass is equal to 30 slug feet per second squared divided by 5.48 feet per second squared. Now our feet per second squared cancel, and we're left with slugs, 5.47 slugs. Now do you see the difference in how you think about it? When we're doing a unit conversion, we use 32.2 pounds mass for every slug to make that conversion. But when we're using the equation of motion, we're using gravity, which is different. And it's different with different bodies. If we're working on the Earth, it's going to be different than if we're on the moon. Let's look at an example. We have a toy car that has a mass of 10 kilograms and it's pushed by a 5-pound force. What will be the car's acceleration, neglecting friction and air drag? We want to find the answer in English units, and we have our conversion factors here. Well, let's start with our equation of motion. Force equals mass times acceleration. We're looking for the acceleration, so we'll solve for that symbolically. Then we can plug in what we know. Our force is 5 pounds, and our mass is 10 kilograms. We'll rewrite our pounds in its basic units, because we would never think of canceling kilograms and pounds. So we'll write our pounds as 5 slug feet per second squared, divided by 10 kilograms. Now, would we consider canceling kilograms and slugs? No, so we have to convert our kilograms into slugs before we can solve the problem. One slug is 14.59 kilograms. Now our kilograms cancel, our slugs cancel, and we're left with feet per second squared, which is an acceleration. Now we can solve for our acceleration, and we get 7.3 feet per second squared. Let's look at this in a different way. Now we have a toy car that has a mass of 18 pounds mass, and it's pushed by a 7-pound force. What will be the car's acceleration, neglecting friction and air drag? Again, we want to find the answer in English units. Well, we use our equation of motion, force equals mass times acceleration, solve for the acceleration, which is equal to force divided by mass. We have a 7-pound force being applied to the object, and it has an 18-pound mass. Now again, I ask the question, would you ever consider canceling pounds and pounds mass? Hopefully not. Pounds mass is the base unit, but pounds is not at a base unit. We can write pounds as slug feet per second squared. So let's do that. We have 7 slug feet per second squared divided by 18 pounds mass. Now, would we ever consider canceling slugs and pounds mass? No, they're not the same unit. We have to have the same units. So we need to convert pounds mass into slugs. One slug is 32.2 pounds mass. Now we can cancel our pounds mass, cancel our slugs, and we're left with feet per second squared. So we have an acceleration equal to 12.5 feet per second squared. Let's talk about static friction and kinetic friction before we move any further so that we understand how this plays into our equations. The static coefficient of friction is represented by mu sub s. This is the friction between two objects that are not sliding, and that friction is always going to be less than or equal to our static coefficient of friction times the normal force. It can be any value between 0 and our static coefficient of friction times the normal force, depending on the applied forces that we have. If, for example, on our two blocks here, if there's no forces being applied, then there's no static friction occurring at the interface between these two blocks. So our friction force is 0. If we apply a force and look at the forces acting on this upper block, we have a weight, we have a normal force, and we have our static friction. If our weight is 100 pounds and our force is 50 pounds, and we have a coefficient of static friction of 0.8, what is the static friction, F? In this case, our static friction, F, is equal to the force that's being applied, which is equal to 50 pounds. In order for it to be static, our forces have to balance. We have a force that's being applied of 50 pounds, and so our friction has to equal that in order to keep the object static. So we have a force of 50 pounds. But what's the maximum force that could be applied without moving the blocks? 50 pounds is not the maximum that we could get. But if we multiply our normal force times our coefficient of static friction, we'll get the maximum force. Our normal force in this case would be 100 pounds, and our coefficient of static friction is 0.8, so the maximum static force that we can get is equal to 80 pounds. Notice that 50 pounds that we've got in this portion of the problem is less than 80 pounds. Again, our static friction can be anywhere between 0 and 80 pounds for this particular problem. What about kinetic friction? When we have kinetic friction, the objects start to move against each other. The kinetic coefficient of friction is represented by mu sub k. Friction between two objects that are sliding is kinetic friction. This can only be exactly our kinetic coefficient of friction times the normal force, and it will always be that value. The maximum static coefficient of friction is usually larger than our kinetic coefficient of friction. It takes a little bit more to get the object moving, but once it's moving, it's a lot easier to keep it moving. Think of pushing a couch across the floor. Initially, it takes a lot of force to get it to move, but once it starts moving, it's considerably easier. You don't want it to stop, because if it stops, you have to apply more force again to get it moving again. But if we can keep it moving, it's a lot easier. The kinetic friction is less than the static friction. If we draw our forces on the upper portion again, like we did on the last problem, and if we have a weight of 100 pounds and we apply a force of 80 pounds, and our coefficient of kinetic friction is 0.7, what is the kinetic friction? Well, in this case, kinetic friction is exactly our coefficient of kinetic friction times the normal force. So we would have 0.7 times 100 pounds, which will give us 70 pounds. Is the upper block accelerating in this case? Well, the sum of the forces in the x direction is equal to 80 minus 70, which equals 10 pounds. So we have a net force. The sum of the forces are not equal to 0. Therefore, it's not static. So yes, we have an acceleration in this case. Let's look at the intuitive meaning of what the coefficient of friction is. Would it be easier to lift or drag this box? Dragging is usually easier than lifting. How much force would it take to lift the box? Well, we'd have to apply at least 100 pounds to get it off the ground. How much force would it take to drag the box? Well, at least 30 pounds, 0.3 times 100. You can think of our coefficient of static friction or our coefficient of kinetic friction as a percentage. For example, it only takes 30% of the weight of the object to start dragging it. Find the coefficient of friction if it takes 10 pounds to barely start dragging the box. Well, if it takes 10 pounds to start dragging the box, then our coefficient of static friction is 0.1, or 10%, which is 10% of our 100 pounds. Is this a slippery surface? In this case, yeah, it's probably a slippery surface because it doesn't take very much force to start it moving. Find the coefficient of friction if it takes 300 pounds to barely start dragging the box. Our coefficient of static friction in this case would be 3.0, or 300%. Is this a slippery surface? No, it's quite the opposite. In this case, the block must be glued to the floor if we have to apply 300 pounds to start moving a 100-pound box. Let's talk about kinetic diagrams. We've used free body diagrams to solve our statics problems. In order to solve our dynamics problems, we need to draw diagrams that represent the motion. Kinetic diagrams are used to indicate the motion of an object. It can be the accelerations or the velocities, depending on the type of problem that we're going to solve. When we use the equation of motion, typically we're going to use accelerations on our kinetic diagrams. We start by drawing the motion at the center of mass. Once we have our free body diagrams and kinetic diagrams, we can use those diagrams to help us write our equations. In this case, the sum of the forces in the y direction is equal to our mass times the acceleration in the y direction. We use the free body diagram to represent the sum of the forces, and our kinetic diagram to represent our mass times acceleration. If we sum the forces in the y direction, we have a normal force minus a weight on the left side of the equation, and on the right side of the equation our acceleration is 0, so our mass times acceleration is 0. In this case, the block is static in the y direction. What if we sum the forces in the x direction? In the x direction we have a positive force F minus the friction, the static coefficient of kinetic friction times the normal force, and that will be equal to our mass times the acceleration in the x direction on the right side of the equation. Once we have our equations, we can solve the problem. Here's an example. We have a 30-pound block that rests on a smooth surface, and a person pulls on the block with a force of 10 pounds. What is the acceleration of block A? Well, first of all, we have to understand what they mean by smooth surface. Smooth means very slippery. For example, no friction. So we have our 30-pound block. We're pulling on it with 10 pounds on a smooth surface. And we want to find the acceleration of block A. Well, our first step in this type of problem is always to draw a free body diagram. No matter how simple we think the problem is, we should always draw our free body and kinetic diagrams to solve the problem. This will help us avoid making mistakes when we set up our equations. For our free body diagram, we have our 10-pound force, and we have a weight of 30 pounds and a normal force of 30 pounds. Again, it's a smooth surface, so there's no friction. For our kinetic diagram, there's no acceleration in the y direction. The forces balance. But in the x direction, we have our mass times the acceleration in the x direction. If we're looking for the acceleration of block A, then we can sum the forces in the x direction and set that equal to the mass times the acceleration in the x direction. Our forces in the x direction are simply our 10 pounds. Our mass is 0.93 slugs, and we have our unknown acceleration in the x direction. Where did this 0.93 slugs come from? Well, we have a 30-pound block. That is a weight. If we divide our 30-pound weight by gravity, 32.2 feet per second squared, then we get our mass of 0.93 slugs. Solving for our acceleration, we get an acceleration in the x direction of 10.7 feet per second squared. Next time, we'll talk about the equation of motion in normal binormal coordinates.